In this video, we are going to be learning about Fischer projections in order to identify a stereoisomer as being a D or L isomer. Okay, so a Fischer projection is a way of taking a three-dimensional object and flattening it in a conventional type manner. And so if we think about our carbon having four different groups around it, I'm trying to draw it where it kind of looks 3D-ish. It has four different groups. Anyway, so we're going to take our eyeball and we're going to look at it from one way. So I'm trying to draw an eyeball here. Maybe give it some eyelashes. Kind of looks more like an eyeball. And we're going to look at it in a way where it's going to become a top view and kind of flatten it. So if we look at it from this way, we can see that like maybe this hydrogen is going up and this one is like off to the side here. So kind of use your imagination to flatten that out. Maybe I'll just switch these letters to match their view of it. So we're going to take this and we're going to flatten it. Now we can see that we can take this and make a cross. And this is a chiral carbon here in the center. It has four different groups on it. And what's going to go up is always going to be our most oxidized group, meaning like our aldehyde or our ketone. That's going to be near the top if we can help it. So for example, if we look at this molecule here, this is kind of a top view of our zigzaggy chain. You can see this bond kind of goes up, down, like that. So it's kind of a zigzaggy carbon chain. So we're looking at that top view zigzag. This carbon down here is not chiral. But neither are several atoms in here. But this is a chiral carbon here. That's our chiral center. And so we take our chiral center. This is a CH2CH3 group off to the bottom. That part of the molecule is not chiral. This one's not chiral either. But because we do have this one chiral center here, as soon as we take the mirror image of it, this molecule will not be superimposable on the original molecule. So these are enantiomers, and we can redraw this as that, and then redraw this as this. And so you can see the H is on the left here, and that H is on the right here. And so these are what we call Fischer projections for those two molecules. So our chiral center is on the center in both of these. And so that chiral carbon is represented by the cross. So let's try to draw a Fischer projection from this wedge dash model. If we take our aldehyde functional group here, it doesn't matter which side I draw the H on. I'm going to have this carbon represents that. This cross represents that one. This cross represents that one. This cross represents that one. And then I have a bottom CH2OH group. Then I can go down the side and write in all my OHs as they appear in the wedge dash model. And there we have our Fischer projection. We can easily count how many chiral carbons we have. We have 1, 2, 3, 4 chiral carbons. We are going to be differentiating between our D and L isomers for this chiral carbon. If the bottommost chiral carbon, so this one's the bottommost If we have multiple, then we look at the bottommost. If there's just one, we're still looking at the bottommost chiral carbon. So we're going to look at the bottommost chiral carbon. If we have this OH group on the right, then it's going to be the D isomer of it. And if it's on the left, then it's going to be the L. So L for left, D for right. And so right means, it stands for dexter. So most people are right-handed. And then L is just left. So here's the joke. This is Samuel L. Jackson, and this is Samuel D. Jackson. And I found this image because it went chiral. It's funnier in person, sorry. Okay. So if we do have multiple chiral centers, we are looking at the bottommost chiral carbon, the one that's farthest away from this carbonyl group. You'll remember that this is an aldehyde. CHO is aldehyde. So if we look at the bottommost chiral carbon, this would be the D isomer of this molecule. This would be the L isomer of that molecule. These are mirror images. So D and L are mirror images. And same here. These two are mirror images of one another. And so since these are mirror images, these are enantiomers. These are enantiomers. If we look at other pairs, like this and that, these are not mirror images of one another, but they're also not superimposable on one another, and so they are diastereomers. So it gets to practice our vocabulary. But we're always looking at this bottommost chiral carbon. Don't look at this chiral carbon because it's not chiral. It has two hydrogens on it, so it's not chiral. Look at the bottommost chiral carbon. Is this molecule the D or L isomer of that substance? Go ahead and tell me. It is the D, because there's our bottommost chiral carbon, and that's on the right. So this is the D isomer. So if we have multiple chiral centers, then we can have multiple different stereoisomers possible. So here's where we have two different chiral centers, and so we have four different enantiomers, or four different stereoisomers total. A and B are enantiomers, C and D are enantiomers, but for instance, B and C are diastereomers, B and D are diastereomers, and so on. C and A are also diastereomers. They are not mirror images, but they are also not superimposable. This is what can happen when you have multiple chiral centers.